Hello, everyone, and thanks for joining the webinar. My name is Ben Sawyer, and I'm the host for today's webinar here at Hazelcast. Today, Marko Topolnik is going to walk us through real-time stream processing with Hazelcast Jet 0.5. Marko is a senior engineer on the Jet core team, which makes him the perfect presenter for today's topic. Get ready to learn, because when the introductory slides are done, Marko will be delivering 2 separate coding demos with time for your questions after each one. And without further ado, I'll turn the mic over to Marko.
Hi, thanks. Introduction is done. I'll be talking about Hazelcast Jet. In few brief words, this is a distributed computation engine which is built on Hazelcast IMDG technology. It's using something called directed acyclic graph to model data flow, but this is kind of a low-level concern. We won't be spending much time on it. And before we go to Hazelcast Jet itself, I'll tell you a few notes about Hazelcast IMDG because it's the underlying technology here, and probably most of you are already familiar with Hazelcast IMDG, but still some context and some important points as we move on to Jet. So IMDG stands for In-Memory Data Grid, which is basically a distributed cache which with more features added on top. It's kind of the product evolved from just a distributed cache to having many more features which were, let's say, low-hanging fruits to add on existing infrastructure you need just to run a distributed cache and the cluster and everything. It has also some computational abilities and additional data structures. One thing I would like to point out here is like the thing that makes Hazelcast stand out in its market segment. It's the simplicity. For Hazelcast, you just need one line of code to start up an instance, and this instance will automatically join the cluster. So if you examine this snippet that we have here, just the first line, hazelcast.new Hazelcast instance, this is all you need to start up an instance on your local gel VM, and immediately behind the scenes, this instance is doing a multicast discovery of nearby other living nodes of Hazelcast, and it will join them automatically and form a cluster. So by the time you reach the second line of code, which is hz.getMapMyMap, you will already be accessing a shared map in the cluster and all its data. And you will also, your node will also have received a part of the data to share its own memory with the rest of the cluster. So your instance will become a part of the cluster. It will offer its CPU resources to the rest of the cluster as well. And in few simple lines of code, you can access and work with the distributed map using familiar operations from JDK, put, get, and from concurrent map as well, put if absent, so some atomic operations. What makes Hazelcast an IMDG and not just a distributed cache? This is a list of features that we also have. There is also distributed list, queue, multibap, and so on. Concurrency primitives. So there's a lot of stuff in Hazelcast IMDG. And one thing that's especially relevant for Jet is its computational abilities, specifically distributed queries and general data processing. So with this point, we'll come back to it a bit later. And now just a few words what exactly it means for Hazelcast to be distributed. Obviously, that means you have several nodes, many JVMs, many instances of Hazelcast acting as a whole, as a cluster, which you from the outside you perceive as one thing, as a single entity. This automatically brings you scalable storage and performance because each node contributes its own memory as well as its CPU cores to the infrastructure available for the whole cluster. It also means elasticity, so you can expand the cluster while it's running. You don't have to shut down everything, reconfigure, and then start up a bigger cluster. You just add more nodes. On the other hand, it also means that you can lose a node, you can shut down a node, and because the data is not just distributed across the cluster, but it's also replicated, the user won't notice this as a loss. Data will just be promoted from backup to primary, and everything will go on as usual. Hazelcast achieves this with data partitioning, which means you break up all your data in some fixed number of partitions, and then the partition is the unit of distribution along nodes. If you add a new node, it will get several of partitions of data from the other nodes. And finally, the part which makes Hazelcast, which is a big part of the story why it's so simple to use, is the discovery protocols that we use. It's so the first option mentioned here is multicast, which is just basic IP protocol that works in any LAN. But we also have specific protocols that work in specific cloud environments, which means you can also easily form a cluster in Amazon infrastructure and others. So moving on to Jet, as we said, this is a distributed computation engine, and it's built on some foundations present in the IMDG, like all the code and infrastructure you need to form the cluster, to manage the cluster membership, which is dynamic. Also, there's the issue of serializing data, deserializing as it moves across cluster nodes. There is the partitioning scheme. We reuse all these elements, also the network stack and so on. There's a lot of technology that we share with the underlying IMDG. And we also, as a separate thing, we can use existing IMDG structures as sources and sinks. And this is very attractive. And we are, in this respect, we are unique in the category of distributed computation engines because we can achieve perfect data locality with this feature. And this boosts performance tremendously if you can fit all the data into the RAM of your cluster. We support both bounded data sources and unbounded. The terms we use in this segment, it's batch. Batch means a bounded job. And for unbounded jobs, we use the term streaming or infinite streams or event streams. The project started in 2015, and we are now almost a year away from the first public release and in version 0.5. And we maintain a quarterly release schedule. So just like Hazelcast, it's as simple to use, as simple to start up, a single jar as well, and it's embeddable inside your existing application. So you don't have to set up a separate cluster. You can just embed your jar into your, for example, cluster web application, and you have Hazelcast Jet running. And another point is that Jet, as opposed to Hazelcast IMDG, has JDK 8 as a minimum, which means we can leverage lambdas, which is very important in this area. Before I go further, I would like to address this very frequently asked question for Jet from our existing users. So we have IMDG, we have some computational abilities in IMDG, so why would I need Jet if I have all this. And the main reason can be summed up that IMDG is more about looking up data, finding it, searching for it, and not so much about full dataset analytics. And this is because in Hazelcast, your main paradigm is place a request and get a response as a result, as a return value of your call. So this means that you get all the data right there in the JVM memory, and this doesn't scale because you have to store everything in a single node. So this is the main difference that we do differently in Jet. We've listed some of these facilities in IMDG. There are some others like executor service which just serve completely different purposes because, for example, executor service is about task parallelism and not data parallelism. Each task runs in a single thread. So, except for the first point that we already mentioned, we have a lot of other advantages. So the first one is that the data flow is no longer to the caller. It starts from the source, gets streamed into Jet engine, and then Jet pushes its data to some sink, which is not the caller. This means that Jet is scalable both in input size and in output size. This is probably the major point to consider. We have more features. For example, we added a new feature in IMDG to support reliable event streams. You can use IMAP or iCache, very similar to Kafka. You can use each map key as a topic you publish your events to, and then Jet can subscribe to these events and get them as a stream. And we also have third-party connectors, which are like industry standards. HDFS is Hadoop distributed file system. This is great for batch jobs. You can load a lot of data which is stored in files, replicate it across a cluster, and then you can read it for a batch job. You can also push data to in the same way to Hadoop. And Kafka is the industry standard for interoperation between systems. It's like a publish-subscribe infrastructure, sort of like JMS, but distributed and low latency and big throughput. So if you work with Jet, you also get Java 8 lambdas. This is very important when you describe computation. It's something you cannot achieve with IMDG. Then there is a completely new field of windowed aggregation over infinite streams. This is just completely outside the domain of basic IMDG, where you don't deal with data that's already stored. You deal with data as it's being generated on the fly. And in this sense, in this case, you need aggregation over a window which is moving all the time. So it's not a fixed batch of data. You have to do your aggregation on the fly with data that comes in, and all data goes away from the window. And all this is fault tolerant, this procedure, because when you're dealing with infinite streams, it's a job that takes an indefinite amount of time, and then fault tolerance becomes a big deal. You cannot just restart the job from the beginning because there is no beginning in infinite streams. So we have support for the possibility that one member that was contributing, that was participating in the computation, it can go away and will remember what it was doing. We can suspend the job temporarily, reorganize the data, redistribute it, and just resume from where we stopped in a fault-tolerant way with no losses. Further to that, what's something that basic computational in Hazelcast cannot do is combining data sources, like an SQL join. You can combine several data sets. You can join them on a join key and make co-group operations. And also you can compose computation, which means you can do, for example, one aggregation and then immediately treat those results of aggregation as your input data set into the next step of computation. Instead of first dumping it somewhere, storing it, and then running another job on it. You just create everything in a pipeline where it just data flows through it. And you can fork the pipeline, which means you can form this intermediate result and then continue computation in several different ways in parallel and reuse the same partial results for each of them. So at this time, let's go to our first sample, which would be a batch job. Let me start a new file. Let's name it first one. Okay, I just have a simple template here that I created for this. I'll slightly enlarge it for you. I think it's okay now. I have some boilerplate lines of code. We set up logging here in the first line, and we start a jet. Now, in this case, for this presentation, I'm using a jet client, and I will separately in the command line, I will start a cluster now from the command line. So this is one node. Okay, it started, and now another node. You can see it will automatically discover. You see here multicast joiner is activated, and it discovers the other node here. So now we have a jet cluster, and now I'll connect to it as a client from here. And what I want to do as the first example is the like the staple of this world. It's called the word count. It's actually a better name is word frequency. And what it means is you've got some body of text material. For example, you have all of Wikipedia or something like this. And you want to find the frequency of each word that occurs in this body of text. This is like common linguistic analysis of text. So to do that, let's make up some mock data. One thing you'll notice is that a jet instance is also an IMDG instance, so I have all the data structures available to it. So I can say jet dot. Let's use a list. List is the simple one. Jet get list lines. We'll put some lines of text here. So let's introduce a local variable for this. Okay, now we have these lines. Let's add some lines in. Also, I'll immediately put here lines clear. So because we are working with a cluster that keeps on going, even after we finish our job, it's if we want to rerun the sample, let's have the things cleared out. Okay, so let's add some lines. Okay, so now let's move up here, and we'll now build a definition of a job to handle this kind of data. I've moved my cursor above the place where I start jet, just to emphasize that the description of computation is not does not need the context of a running jet instance. it's just a plain data object you create locally. So we start with pipeline. This is our main entry point into the API. We call it a pipeline. The basic paradigm is here that you attach the pipeline is something that data flows through, and you attach various stages to the pipeline, and each stage does some computation and then emits its results downstream. So first of all, we need to well, it's easy when you see the methods. There's just one method to call, except toDeg, which is not important now. Draw from. We have to draw from some source. That's how we start our pipeline. And in this case, we want to say, I want to draw from my list. So sources list, like this. We can show you the name. Like this. And let me add some type safety here. It cannot know in advance that it's strings. So now we have the source, and now we attach some computation. So first of all, we need to split these lines into words. So basically you have to transform a single line into a series of objects. This is a flat map operation, which you may know from Java util streams, and we just need to provide the lambda that will split it. So we transform line into line split. This is a regular expression. It says split at any non-word character, but we also have to add here something else. The result of flat map operation must be our traverser, which is like an iterator, but a simple kind of iterator we use. We say traverse array. Okay. So now we have the flat map stage. We can see what's the type of it. It's again a stream of words. Now we have to group those words so we can count them, because we want to get a count of all the distinct words. So we say words group by. So what do we group by? We group just by whole word. So we have a function actually for this, which is called whole item. We group by whole item. And now we have to say what kind of aggregate operation we want to perform on all the words in a group. And yes, we are counting them, so counting. Aggregate operations counting. This is a built-in operation. You can also define your own aggregate operations, but this one we have provided. So like this. Now let's see what we got. Counts. So we got a stream of map entries from key is string, this is the word, long is the count. So basically we're done now, and now we have to put this stuff somewhere where we can inspect it, because as I said, Jet wants to take data from a source and put it into some sink and not push it to you. So let's say words and counts, and we're gonna drain to sink. Actually, yeah, okay, sinks, and we'll use a Hazelcast map for it. Like this. So that's basically it. We have our pipeline now. Now we have to we'll get it running. So one thing to note is that you see this pipeline was actually involved directly just in this first line where we draw from source, but actually all these other stages are automatically registered with the pipeline. So all this code that we wrote where we don't mention the pipeline directly but just stages, they all inside actually get registered in the pipeline. So the pipeline contains everything that we described here. So we say here jet.newJob of pipeline, and we say we want to join the job. This means we'll wait for the job to complete before we go on. We cannot get the result from the job itself. The result is in the map. And there's one more thing here. Because I'm now a client of Jet, I have to actually explicitly tell this job to add my class that we are just creating to the job as a resource, because it contains all these snippets of code. All the lambdas we use here, these are actually transformed into methods on this class, and so we need Jet will need our class to be able to deserialize our job definition. So we say new job config add class first. Okay, so now the job will run, but let's also add some code to inspect the results. So our map was called like this. So let's say jet get map version counts, and we can just print it. But you cannot print the map directly because it's just a handle to a distributed map. But if we say .entry set, then this will actually fetch all the entries of the map. So let's see, and yeah, let me clear the map. As cleanup. Okay, so let's see if we can run this. There we go. And we can see back what happened on the cluster. This is the log. This is the, I'm showing you the window where I started the cluster earlier. You can actually see here the direct acyclic graph that was, so our pipeline was converted to this DAG, direct acyclic graph, and these are the vertices and edges in it, and then Jet executed the job, and we got the result here. So you can see there's 111 and hello and world occur twice, and that's it. That's our job. At this point, I can finish with this, and maybe this is a good place to maybe answer some questions you have right now about so far the code or anything I've said so far. Yeah, there is one question now from Balaji. How did the client know which Jet cluster to submit the job to? Well, that's a part of the philosophy of simplicity of Jet. If you don't supply any particular configuration, we'll automatically look for some Hazelcast Jet node on the local machine. If this was another machine, you'd have to supply the IP address. But this is just convenient to start playing around with Jet without having to fiddle with configuration. There's another question from Tao Lin. Does Jet support declarative rule specification? I'm not so sure what this means. Maybe this means something like what we have in rules. like a rule-based engine, production engine, or something like Prolog. We don't have this feature right now, and we didn't think about it. There's always this point: can it be distributed? So that's the first point where you have to ask yourself whether it makes sense for a certain paradigm to be used, whether it is possible to profit from a computation engine whose main feature is that it's distributed. So we might consider this, but I cannot give you the answer right now whether it will make sense, whether Jet will bring anything more to the table as opposed to a single node processing. Another question from Jay Yang. Does Jet support sliding window? Yes, it does. As of our current version, unfortunately, you cannot access this functionality through the high-level API that we're demonstrating, but you can access it through the core API because all the functionality is there. It's just that our release schedule is such that we didn't have time to complete the pipeline API in 0.5, and this is the plan for the next release. So 0.6 will support sliding window definitions through the high-level API that I'm talking about. Okay, another question. After this question, I'll go on to the next sample. We have one more sample which is about streaming. So Pilupal asks, can you explain how its use Hazelcast IMDG cluster helps Jet in analytics? The main point is that if you have data already stored in a Hazelcast cluster, if you're a user of Hazelcast cluster, it will be first very easy to set up a computation, an analytic computation with Jet, and second, it will be as opposed to the data, let's say, being in some other system like Hadoop file system, you will get about a 5-time performance boost from the fact that you have it in RAM and you access it directly on the member with no network involved. So this is the main, these 2 main points: simplicity and performance. And now I'd like to go on to the next sample, and then I can go back to the questions. So before I go to the sample, I can also show you this graph, this performance chart. We measured this for exactly the kind of job we just demonstrated, word counting. I mean, word count job, pretty much exactly the code you saw we used for the benchmark, and we also made the same kind of code for competing products in the area of distributed computation, which is Spark and Flink. And you can see that the green bar, which is by far the largest bar for throughput in the left chart, is Jet when using IMAP locally. And you can see the blue bar, which is Jet but using Hadoop HDFS. And Spark and Flink are also set up with Hadoop. So you can see that Jet leads the others by significant. So we are not talking percentages, we're talking factors. 3-4 times better performance with the same kind of source. And if you use in-memory source, IMDG native source, you get another factor of 4 boost towards Jet with Hadoop. And if you note there are 4 measurements performed. There is 2 numbers for each measurement, input data size and output data size. On the second graph, you can see that we have 10 times the input, and in this case it didn't fit into RAM, but you can see that the input data size doesn't matter for throughput almost anything. And then with the next two, you see increasing output data size going to 10 million and 100 million distinct keys. And here you can see that output becomes the bottleneck. Speed of writing to output to HDFS becomes the bottleneck, and performance throughput decreases. This highly depends on your SSD. But you can also see that in each case, Jet has a significant advantage over others, and Spark was apparently not even able to finish with those larger output sizes. So let's go to demo number 2. In this case, we are doing a streaming job, and now I have some boilerplate code to set things up, because we have to set up an infinite stream of events, and we are using some mock event generator. This is the model is stock trading. So here you can see the loop which will be generating events. First we do some waiting here, and then so each 50 milliseconds we produce one trade item, trade event, and the trade is a very simple object. It just has some IDs in it and no real data. It just has basically its own primary key and two foreign keys for products and brokers. So we want to enrich this stream of trade events with the actual data hiding behind those IDs, and this is what our job is about. This is called data enrichment. Here you can see that we have a method that prepares some enriching data. So we prepare some brokers and products as full objects. These are some names for the products and brokers. We put them all into Hazelcast maps. Here you can see these two lines fetch those maps. And we also didn't mention that here, how do we publish these events? This is what I mentioned earlier. We just put the trade to the same key. We use just some arbitrary key in the map, and we just put trade on the same key every time, and this generates an update event in our event journal. So now we're going to write the code to enrich this stream. First of all, we have to create all those sources. Let's start with trades. We draw from map journal. So this is an infinite stream source. We name it trades. We have this as a constant. Trades. And then we supply some transformations on it, because we don't want to deal with raw events. So you can supply both a filtering operation, which will be performed at the source before generating any traffic. In this case, for filter, we'll use just pass-through filter, always true. And now we have to specify a projection function, so we extract the interesting data, because we are not interested in that key, which is constant, so we just want to get the value. So we say entry value. And finally, the third parameter here is whether we want to start receiving everything that's in the map journal, so all the history, or just from the point where we connect. And in this case, I'll say true, which means only from the point where I connect, because if we have a running cluster, so it will have some old data in it. And now we have some problems. Some map type inference problems, I guess. Let's see if this fixes it. I'll copy it from this, so let's not get bogged down on this detail. So yeah, I used entry.getValue, but actually I had to supply, because I don't get map entries, I get event specific types for events. So anyway, now I have set up the trade source. This is my infinite stream, and it's just a stream of trades. And now we set up the enriching streams, which are finite streams from those maps, which we generated earlier. So we say, so you can see we can start several times from the beginning, from the method draw from. So it's going to look like this, but I'm now going to copy the full expressions again to save us some time. So we just added some generic types to what I had before. So now we have three streams. One is what we call the primary stream. This is the stream we enrich, and two streams which contain the enriching data. So now we have a specific operation. We start with the primary stream and we call hash join. This is a specific join operation which is made just for, it's specifically tailored for this use case of enriching streams. It means that you use something in SQL terms. It would be joining on a primary and foreign key. So our trades, if it wasn't a table in a relation database, it would have a primary key and two foreign keys, and we'll use these foreign keys to join with the other tables. So first we join the product entries, and now we have to supply the join clause information. So we just have to say how to extract the key from, so where is the foreign key? We have to identify the foreign key, the primary key, and a function that will extract the actual enriching item from the enriching stream. And actually we have a simple way to do it. We call join map entries, and we now just have to provide the foreign key from the trades, and this is trade product ID. So what we did here, you can see what we created is a join clause. We can just briefly study the Java doc. The join clause specifies these three things which are needed to compute the join. Left-hand key extractor, this extracts from the primary key, so this extracts the foreign key from the stream to be enriched. Right-hand key extractor extracts the primary key from the enriching item. And finally, the projection function, it takes the enriching item and it takes what it got in the stream and then extracts the actual part that we are interested in. Because if you get map entries, you're not interested in the full map entry, but just the value. That's the enriching data, actually. So with that in mind, we can go back to the sample. So we are hash joining on product entries and foreign keys product ID in trade. And then we repeat this, but for broker entries. and we also say join map entries, and we have broker ID. So that's about it. This is the hash join operation. Let's see what's the type of this. What did we get? We get a tuple or a tuple of three things: the trade from the primary stream and the two items that we joined into it. And so now we can just process this stream. For this sample, I'm using a simple list output. So we'll drain to a list, and we'll just put some what we call news lines. So we'll just have statements in plain English about this trade. So we say joined, we'll map it to string. Take this tuple, and let's just get some string. Let's say so we'll first supply the ID of the trade. So we have to say tuple f0. The field 0 is the trade ID. Then we say which broker traded which product. So we have tuple f2. Field number 2 is broker. We use its name. And we have f1. Field 1 is the product. And again, just name. So this is it. I can drain it right away. Drain to things list trade news. So this is it. We perform the hash join, and we are draining to the list. And here we already have the supporting code, which will prepare the enriching data. Just put that static stuff into the Hazelcast maps. It will start the event generator, which we explained. The trade news, this is the list, that's the sync. We are starting the job. Just giving it some time to settle before we start generating events, so that we don't miss anything, because we said we're just going to observe the events generated after the job started. We generate events for 5 seconds. This is a simple method that puts this enabled flag to true. This allows the code to get to this point at all, otherwise it's just looping with no action. So we enable it, wait for 5 seconds, disable it, and that's it. That's what this method does. Then we cancel the job, because it's an infinite job, it's an infinite stream, it will never end on its own. And then we'll just inspect what we got in the list. So let's start it. Okay, so what happened was we just reported our static data here. Then we started the job. We started generating the events. You can see we are publishing trades. It just has some IDs inside. We published them, about 100 of them. And then we stop this and analyze the results in the list. And you can see that some brokers traded some random stocks. And of course, we could have let this job run indefinitely, and it would just keep emitting those trade news. And if we used something better than a list sync, then it wouldn't accumulate everything in RAM, but it would be made available to some downstream facility that observes this news. So this ends our second sample. let's see if we have more questions now. I'll open my Q&A box. So one question was from before. You can ask more questions given the new sample. Mandar Redic asks, do you have any business scenarios or case studies where Jet is used? We have some customers, we have some contacts with prospective customers who are interested in Jet. Things are revolving quite a lot about just this topic of data enrichment. This kind of pops up many times as an important use case, and also data analytics of IMDG data. If you have more questions, please post them. We have about 10 minutes. Okay, Taolin asks, before stopping the job, can I get an iterator out of the sync list, then iterate through the result? Well, a list is not such a great object for streaming jobs. We just use it because it's the simplest thing to demonstrate. But, well, I'm not sure about the semantics of the list iterator. Maybe it's okay to get an iterator while the list is updated. I cannot say for sure. It's quite possible. But the main point is that you shouldn't really use a list in production, because all of the list is stored in a single partition. So it's basically not really distributed, because everything goes to the same member. A map is much better because it's a distributed sync. But as long as you are dealing with infinite data, you should not store to a source, to a sink, which just keeps everything forever. You should use some kind of publish subscribe with eviction. Balaji Rajagopalan, sorry, it's not so easy for me to pronounce long surnames, asks, can the infinite streams be a Kafka topic? Yes, so we support Kafka both as a source and a sink. Balaji also asks, does Jet have native support for Kafka? Yes, we have this built in, and you can use it already. Jet data, I'm not so sure. Taolin asks, can you talk about Jet DR scenario? But I'm not sure if I know what the DR means here. Is it enrichment or? Anyway. So Visagan asks, how does Jet connect to HDFS? Should it be run on Hadoop as MapReduce, or should we run Jet as an external client and connect externally to Hadoop? Actually, the best way is to collocate both clusters. So if you have a Hadoop cluster and you should start on each of the members, you should start a Jet member, so then Jet will figure out automatically which slices of data are local, and it will access them locally without sending over the network. I hope this answers the question. And we have this in code samples, I believe, Hadoop samples. So I think Taolin asks about disaster recovery. So I don't know what kind of disaster you mean, but if one node fails, as I mentioned before, you can set up fault tolerance. You can set up exactly once processing, and this means when a node fails, the job is suspended until we reconfigure automatically, redistribute the computation on the existing, on the remaining members, and then we just go on processing with no losses. Jay Yang asks, how can we turn a map listener into a source? Now, map listeners, this is an event listener. This is not the best mechanism because it can lose events if the cluster is under high pressure. This is why we introduced the special new feature of map journal, which is an inside. It's an SPI level feature, so it's not a public API, and Jet uses this SPI internally. So we have sources which I just demonstrated, a map journal source, and that's the way you should use Hazelcast IMAP. Balaji asks, how does a pipeline behave if we have a distributed Jet cluster? Well, I demonstrated this now on 2 nodes. Well, they're only running on my laptop, but conceptually it's the same. These two nodes don't really know they are on the same machine. They talk to each other over TCP/IP. They have each its own process with its own memory. So what I demonstrated actually already is a distributed Jet cluster. So the pipeline is meant for it. It works. We designed everything for it to work. One thing you have to always keep in mind is that you have to ensure your pipeline can be serialized and distributed across the cluster. So that's why we had to say add class to the job. Okay, I think this is it for the questions. I have some more performance benchmarks to show you. This is for similar job that we built now. It's for stock trading, but it's actually doing a sliding window aggregation, which is more complex than just data enrichment because it aggregates data over a time window. And you can see here the latency as opposed to throughput. So on the x-axis, we define the throughput, and on the y-axis, you can see the latency for this throughput. And you can clearly see that Jet is far faster, has very much lower latency than the competition. It's like at very low throughputs, it's 4 times, I'd say. 4 times lower latency, whereas as throughput increases, latency explodes with Flink and Spark, whereas Jet's latency actually gets lower. So with 5 million messages per second, we still didn't reach Jet's bottleneck or point where it would show increase in latency. Yeah, let me go to the roadmap now, a very short description of what we plan to do next. So we have 0.5 out. The plan is to release 0.6 by March, maybe even in February, but a safe date is in March 2018. And the major thing that's missing and that we want to add is completed story for the pipeline API, because currently we are missing the windowing part. We'll also add job elasticity, so it means if you add a new member, it will automatically become a part of running jobs. And we have quite a lot of focus on documentation, because Jet, obviously it's a new product. It's not just evolving, it's more like growing and sprouting, so it's very difficult to follow all this development with good documentation, and this is something we have in focus and plan to improve a lot over the next release cycle. And by the end of 2018, we hope to reach maturity to be able to release 1.0 release. So yeah, that's about it. We are just on time. Yeah, I think this is a good place to end. Thank you.